I'll show you stuff that's published, not the 20,000-fold better, because for this audience, I think we'll stick with the stuff that's well established. We're detecting cancer markers somewhere in this nanomolar range, which is right where we need to be for detection of cancer markers in urine. In cases of people who have prostate cancer, patients who have prostate cancer, they will have nanomolar concentrations of cancer markers in their urine. So we're actually right in the ballpark of where we need to be. And the developments that I alluded to earlier, the thing about making things much smaller and improving sensitivity 10-fold or improving sensitivity 20,000-fold is where we need to go to make the sort of sensitivity that we need to actually detect cancer markers early. So that's where we're going. OK, now, it turns out when you do these sorts of experiments, and our goal here is to develop a cancer diagnostic, you also learn quite a bit about how biology and chemistry work. And I want to give you some glimpses of that, the sort of fundamentals that come out of these sorts of investigations. One thing we asked ourselves very early on is what is the mechanism for this detection? Why are we getting such good signal-to-noise ratios? And one thing we figured out was actually the detection of binding is actually due to disruption of salt ions as they come down to the electrode. Okay, so we have this sort of kelp forest of viruses. So imagine all these viruses waving in the wind. And then when things bind to those viruses, it actually blocks the transport of ions down to the electrode. And in doing that, we can actually detect that. That's that signal to noise that I showed you earlier, the identification of the cancer marker. Now, it turns out this is also, this basically gives us a mechanism for developing better sensors. But it also has inadvertently shown us something fundamentally important about how viruses themselves work. While doing these experiments, we frequently regenerate our electrodes by dipping them in acid. Okay, and acid, of course, has a low pH. And when you dip the electrodes in acid, it will release any binding proteins that are attached to the surface. And we were surprised that when we did this, our electrodes, our sensitivity vanished. And we actually uncovered a new type of motion by viruses in this way. So we were surprised to find that viruses actually curl up when they encounter acidic solution. This is something actually that hadn't been seen before, at least to my knowledge. And here's some evidence of this. This is a different kind of experiment called dynamic light scattering. We're basically looking at the shapes the viruses have and under different pHs. So here is pH 7, the pH that your bodies are at. Okay, so this is just biological or physiological pH. And viruses are generally extended at this pH. This is the big peak over here. As the solution gets increasingly acidic, the viruses start to coil up. And we actually think that this is related to the survivability of viruses in your stomach. It's one of the ways that these viruses have evolved to survive low pH conditions, such as what are found in your stomach, and get down to the bacteria where they need to infect. So they actually will curl up onto each other, onto themselves, into tiny little tight balls that we've actually seen by atomic force microscopy. And in doing so, they avoid being digested. That's actually the latter part, the avoid being digested, is a hypothesis that we're currently testing.